Welcome back. I am the Body Whisperer, and I am glad you are here. Before we begin, let us settle in together. Find a comfortable position. Let your arms grow heavy, your legs, your shoulders. Take a slow breath in and let it go. One more, in and release. Good. Now, while you rest here doing nothing at all, something quiet is happening inside you. Your body is working. It always is. Every hour of every day, without ever asking for thanks. I want you to get to know it a little better, to listen to it, to feel it, to appreciate it. Because the more you understand the quiet world beneath your skin, the more at home you feel inside your own body. So, come and meet Mitochondria Mia. One small part of you that keeps working through the night while you sleep. This is the story of 2 hours of mitophagy and cell energy to fall asleep to. There is nothing you need to do now, nowhere to be, nothing to figure out. Just breathe. Close your eyes if you have not already, and let us begin. There is a quiet piece of work going on inside you right now, and it has been going on every night of your life. Not the breathing, not the heartbeat, those you know about. This is smaller and in some ways more patient. It happens at the level of the cell itself, inside the tiny engines that keep every cell alive. Let the shoulders drop. Let the jaw go soft. There is nothing you need to do. The work is already underway. Every cell in the body runs on energy, not wishes or willpower, actual molecular energy. A small chemical called ATP, which stands for adenosine triphosphate, though the name matters less than the idea. Think of ATP as a tiny charged coin. When a muscle fiber pulls, it spends a coin. When a nerve fires, it spends a coin. When the heart squeezes, another coin and another, 60 times a minute, all day, every day. The coins have to come from somewhere. They come from the mitochondria. A mitochondrion, one of them, is a small enclosed structure that lives inside almost every cell of the body. Its job, its whole reason for being, is to take fuel, glucose from the food you ate, fat from the stores the body carries, and combine that fuel with oxygen to make ATP. The process has a long name, oxidative phosphorylation, but the plain idea is simple. It is a controlled burn, producing energy the cell can actually spend. A single cell can hold a handful of mitochondria, or many thousands, depending on how much energy that cell needs. Heart cells are dense with them. Working muscle cells pack them close. Cells that do not ask much carry fewer. The arrangement is practical, almost elegant. And now, while the body rests, one figure moves through all of this. Her name is Mia. Mitochondria Mia does not make the energy herself, though she is by nature one of the things that does. What she does on a night like this is something closer to management. She walks the floor. She checks the stations. She runs the audit that the daytime hours are too busy, too loud, too full of urgent demand to allow. She has the whole night, and she knows it. Her steps are slow and even. The kind of steps that belong to someone who has done this work so many times that rush would seem almost disrespectful to the quiet around her. Here is the thing about a mitochondrion that nobody thinks to mention. It wears out. Like any engine run hard enough, long enough, it grows less precise. The membranes that should hold a tight seal begin to leak. The proteins that carry electrons down the chain begin to slow. A mitochondrion that was once an efficient converter of fuel to energy becomes, over time, something closer to a drain, pulling in fuel, producing less ATP, and leaking small reactive molecules called free radicals as a byproduct. Free radicals are not villains exactly. They are simply unstable. They are a normal byproduct of any combustion process. But in excess, leaked from a worn, inefficient engine, they accumulate and begin to interfere with the delicate chemistry around them. A tired engine left running is, in the end, worse than an engine taken offline. Mia knows this. So the work of the night is not simply to keep all the engines going. It is to know which ones should keep going and which ones have given enough. It is to mark the worn stations for recycling so that their parts, their membranes, their proteins, the raw materials they still hold, can be broken down and used to build fresh, efficient ones. The old making way for the new, not loss, renewal. This is called mitophagy, from the Greek for self-eating, though the name sounds stranger than the process. It is the cell's own quality control. Specific, deliberate, unhurried. It does not sweep everything away. It targets the ones that need to go, and it runs best here, in the quiet. The reason is simple. When the body is active, running, thinking, digesting, managing the small fires of a full day, the cells need every engine they have, worn or not. Demand fills the available supply, and then some. Taking a mitochondrion offline in the middle of all that would be like pulling an engine from a ship while it is crossing open water. But now the ship is in harbor. The sails are down. The hold is still. This is the honest reason. Rest is not nothing. It is the window, maybe the only reliable window the body gets, to take the failing parts offline without cost, to do the maintenance that full daylight hours cannot afford. The body is not idle while you sleep. It is finally free to be honest about what needs replacing. Mia walks slowly through the dim interior of the cell, reading the stations the way a mechanic reads an engine, not by what it looks like, but by what it is doing. The voltage across its membrane, the signals it is sending, the small chemical flags that warn mitochondria raise, almost involuntarily, when they begin to fail. She is not rushed. She is not worried. She has done this 1,000 nights, and she will do it 1,000 more. The breath slows. The room is dark. Somewhere inside the chest, the heart keeps its steady count. And Mia keeps walking. There is nowhere else you need to be. Nothing you have forgotten. The night is long, and it belongs to you. Somewhere inside the chest, the heart keeps its steady count, and Mia keeps walking. She walks a floor that most people never think about. Not the floor of a room, not a hallway, not any space you could draw a map of. The floor she walks is the inside of a single living cell, which is smaller than a grain of sand, and yet if you could unfold everything packed inside it, would astonish you with how much it holds. And what it holds above almost anything else is machinery. The mitochondria are the engine room. Each one is a small enclosed structure, its own walls, its own interior, its own set of working parts. A cell that works hard, like a heart muscle cell, keeps a great many of them. A cell that is mostly quiet keeps fewer. The number shifts depending on what the cell is asked to do, and the cell is pretty good at reading that demand over time. Here's what those engines actually run on. The body breaks food down into simpler forms: glucose from carbohydrates, fatty acids from fat. Those simpler forms arrive at the mitochondrion like raw materials delivered to a factory gate. Inside, the mitochondrion takes them apart further, pulling electrons loose from the molecules the way you might unwind wire from a coil. Those electrons don't just drift away. They get handed down a chain, a series of proteins lined up along the inner wall of the mitochondrion, like relay runners passing a baton. This handoff, this long, careful relay, is called oxidative phosphorylation. It is one of the oldest chemical processes in living things. At the end of the relay, the electrons meet oxygen. That meeting releases energy. The mitochondrion uses that energy to spin a tiny molecular machine, something that works almost like a turbine. And that spinning builds a small molecule called ATP, adenosine triphosphate, if you want the full name. ATP is the currency almost everything in the body spends. A muscle contracts because it spends ATP. A nerve fires because it spends ATP. A cell divides, a protein folds, a membrane pumps. All of it costs ATP, and the mitochondria are the ones making it. Mia knows this. The body holds around 37 trillion cells. That number belongs to the cells, and to the cells alone. Each of those cells carries its own collection of mitochondria. Some carry only a few. Others, the hardest working ones, carry thousands. The heart muscle cells, the liver cells, the cells in the muscles you use to carry yourself through the day, they are dense with them, packed like boiler rooms below a ship's deck. But here's the thing that changes the whole picture. A mitochondrion is not a permanent fixture. It is not welded in place. Every time it runs the electron relay, small reactive molecules are produced as a byproduct, a kind of exhaust. These are called reactive oxygen species, or if you prefer plain words, unstable particles that want to react with whatever they touch. In a healthy, efficient mitochondrion, the production of these particles is modest, and the cell has ways of managing them. In a worn mitochondrion, the relay becomes leaky. Think of a garden hose with small holes in it. Water still comes out the end, but pressure drops, flow drops, and the water escaping through the holes does not go where it was meant to go. A leaky mitochondrion still produces ATP, but it produces less of it per unit of fuel, and it releases more of those reactive particles in the process. It is not just inefficient. It is actively adding to a problem the cell is already managing. This is the part that matters most, and it is easy to miss. An old mitochondrion running badly is not neutral. It is not simply coasting. It is drawing fuel, producing exhaust, and delivering less of what the cell actually needs. The cell pays the same operating cost and gets a smaller return. Left running long enough, a collection of worn mitochondria changes the whole character of a cell. The cell works harder for the same output, and the reactive particles accumulate, and the damage spreads slowly outward. Nobody announces this. There is no signal the body sends you. It happens at the scale of molecules, quietly, across years. This is precisely what Mia is here for. She is not here to run the engines. She is here to decide which ones are still worth running. Her job on this audit is not production. It is honesty. She moves through the cell and reads the signs, the subtle chemical flags that a worn mitochondrion raises without knowing it. Changes in its membrane, changes in the voltage across its walls, the slow drift in markers that a healthy one would not show. She reads those signs the way an experienced mechanic reads a sound, not loud enough to name, but wrong in a way that is unmistakable. And when she finds one, she does not hurry. She marks it. She moves on. There is a whole floor still to walk. Ollie, who mops up the reactive particles these worn engines leave behind, passes her in the corridor sometimes without a word. They understand each other's work. He cleans up what gets loose before Mia arrives. She removes the source so less gets loose in the future. It is a neat arrangement, unhurried, unglamorous. Not a rescue operation, just a quiet reckoning. There is no next thing. Nothing waiting on the other side of this moment, just the weight of the blanket and the slow, easy breath. Not a rescue operation, just a quiet reckoning. And so Mia walks. She moves through the cell the way a careful inspector moves through a building after hours, not hurrying, not looking for drama, but reading the small signs that accumulate when no one is watching. A gauge slightly off, a hum that used to be steady and isn't quite, a door that no longer closes flush. None of these things would stop the building from standing. But a good inspector knows they matter. Mia is a good inspector. Here's the thing nobody explains when they talk about worn-out mitochondria. The problem is not simply that an aging power station makes less energy. That part is true, but it is only the beginning of the story. The deeper trouble is what it does with the fuel it is still burning. A healthy mitochondrion is a clean engine. Fuel goes in, glucose, fat, and the process of turning that fuel into usable energy, which runs along a chain of molecular steps inside the inner membrane, is remarkably controlled. The electrons move in an orderly relay. The chain passes them along, step by step, and at the end, oxygen accepts them. That final handoff is what produces water as a byproduct. Tidy, efficient, almost nothing spilled. A worn one is different. The inner membrane of a mitochondrion, the folded wall where most of this relay happens, begins to lose its integrity over time. Small leaks open up. The electron relay, which should run in one careful direction, starts to shed electrons sideways. Those escaped electrons don't disappear. They collide with oxygen molecules nearby and produce something more reactive, more restless, compounds called reactive oxygen species, sometimes shortened to ROS, which are essentially unstable fragments of oxygen that are looking for something to bond with. Think of a tiny spark landing on a dry floor. Usually it goes out, but if there are enough sparks, and if the janitor is not keeping up, the floor starts to show damage. Ollie, the cell's night janitor whose whole job is neutralizing exactly these reactive fragments, would recognize that description immediately. He works tirelessly through the sleeping hours, sweeping up what the mitochondria shed. On a good night, with healthy power stations running cleanly, his work is manageable. On a night when too many worn units are still running, his work becomes something closer to triage. But Ollie's work is its own story. What matters here is what Mia sees. She sees a mitochondrion that is producing more reactive oxygen species than a healthy one should. She sees the membrane potential, a kind of electrical charge that runs across the inner membrane and drives the whole energy relay, sitting lower than it ought to be. A healthy mitochondrion holds this charge the way a fully wound watch holds tension. A failing one is partly unwound. The mechanism still turns, but less is produced per turn, and more is lost to friction. Low membrane potential is one of the primary flags Mia reads on her audit. It is the cell's own honest accounting, not a label anyone applied from outside, but a real physical condition that the mitochondrion is broadcasting through its chemistry. The cell has proteins that sit nearby and sense exactly this. When the charge drops below a threshold, a protein called PINK1, a kind of molecular sensor that normally gets quickly cleared from a healthy mitochondrion, begins to accumulate on the outer surface instead. It cannot be cleared because the machinery that would ordinarily clear it depends on the membrane being healthy. And it calls for a second protein called parkin, which arrives and begins attaching small molecular tags to the mitochondrion's outer surface. Those tags are a language. They say, "This unit is ready to be processed." Mia knows this. It is not a punishment. The tags carry no urgency and no judgment. They simply communicate a state, the way a colored flag on a map says here. not alarm. The cell reads them, and the recycling process, the one belonging to Alex, the facility manager who only opens his doors when the body is fasting or deep in sleep, can begin. Alex does not rush. That is not a criticism of his temperament. It is a description of how his process actually works. Autophagy, the cell's broader recycling system, of which mitophagy is one specific branch, aimed only at mitochondria, requires the cell to be in a low-energy demand state. When the body is awake and active and eating, the cell's resources are pointed outward, toward performance. The recycling lines are there, but they run slowly, like a factory floor where the main production line takes priority, and maintenance gets scheduled for later. Later, here, is now. As sleep deepens, demand pulls back. The signals that keep the cell in high output mode quiet down. The chemistry shifts, and Alex, who has been waiting with professional patience, begins to move. He sends the membrane. That is the key step. A double-layered structure called a phagophore begins to grow around the tagged mitochondrion, cupping it, then closing completely around it. The worn power station is now sealed inside a new envelope, called an autophagosome, which will eventually merge with the cell's own digestive compartment and break the old machinery down into its components. Those components are not discarded. That is the part worth holding on to. The amino acids, the lipid fragments, the raw molecular material, they are returned to the cell's common supply. From them, given the right conditions, new mitochondria can be built. Younger ones, tighter membranes, cleaner relays. The old engine does not just stop. It becomes the raw material for the next one. It did not make the process simple. It made it generous. Let your chest rise and let it fall. Slow and unhurried, like water moving over smooth stone. There is no effort in it anywhere. There is a moment, somewhere around the first hour of real sleep, when the cell's demand for energy begins to ease. The urgent messages from the outside world have gone quiet. The muscles are still. The mind has let go of its lists. And in that quiet, something shifts on the cellular floor. Mia feels it before she can name it. A loosening, room to work. But Mia does not work alone. She never did. There is a molecule that moves through the cell like a delivery runner, carrying electrons from one station to the next. A molecule called NAD+, which stands for nicotinamide adenine dinucleotide, though nobody in the cell ever says the whole name. They just know her as Nancy. NAD plus Nancy is not a machine, exactly. She is more like a current. She picks up electrons at one point in the energy-making process and drops them off at another, and nothing in the chain moves without her. The electron relay that produces ATP, the cell's usable energy, depends on Nancy showing up, loaded and ready, again and again. Oxidative phosphorylation, that careful step-by-step handoff of electrons described in the earlier part of this night, could not run a single turn without her. Mia knows this. Here is what nobody says plainly enough about NAD+. She is not just a fuel carrier. She is also the activating signal for a whole family of repair enzymes, proteins called sirtuins, whose job is to keep the cell's genetic material tidy and its energy stations honest. When Nancy's levels are high, the sirtuins run. When they run, quality control signals get louder. When those signals get louder, Mia's audit becomes more sensitive. It is a loop that feeds itself. More Nancy means more sirtuin activity. More sirtuin activity means more precise flagging of worn mitochondria. And worn mitochondria flagged with precision are the very units autophagy Alex can process cleanly, without losing usable parts in the confusion. Nancy does not explain this. She is too busy. She simply passes through the audit station, drops her electrons, and moves on to the next reaction. There is something else about her worth sitting with. NAD+ does not hold steady across a lifetime. The levels that run easily in a young cell take more effort to maintain as the years pass. The cell does not announce this. It simply finds that the sirtuin signals grow softer, that the flags go up a little slower, that Mia's audit takes a little longer than it used to. The cell adapts. It always does. But it adapts more smoothly when the conditions are right, when fasting has begun, when sleep has deepened, when the body has stopped asking for new energy and turned its attention instead to what is already here. That is where the night earns its keep, not as a pause, as a condition. While you sleep, Nancy is not resting. She is cycling, picking up, dropping off, picking up again, threading through 100 reactions that could not happen while the body was busy burning fuel for motion and thought. The fasting state that settles in a few hours after the last meal tilts the chemistry just enough that cells begin to shift from production to cleaning. NAD+ dependent pathways that sit low during the busy hours of the day become more active. Sirtuins that were waiting on the bench come onto the floor, and Mia walks the floor with a sharper eye. A worn mitochondrion leaking reactive oxygen species, those small, unstable molecules that damage what they touch, is not just a poor energy producer. It is a source of noise. It is generating a low-level chemical static that can interfere with the very signals Mia depends on to do her work. The janitor Ollie, who spends his nights mopping up exactly that kind of damage, calls leaky mitochondria his primary crime scenes. He does not mean it unkindly. He is simply precise. The connection between Nancy and Ollie's work is closer than it looks. When NAD+ levels are adequate and sirtuins are running, one class of repair enzyme, the PARP family, which patches breaks in the cell's genetic thread, also gets a share of Nancy's attention. PARP repairs are expensive. They can draw heavily on the NAD+ supply. In a cell under a lot of oxidative pressure, PARP and the sirtuins are quietly competing for the same resource. This is not a conflict that needs resolving by the narrator. The cell resolves it through the night, slowly, as conditions ease and Ollie clears the damage that was driving PARP to work so hard in the first place. Less damage to patch, more Nancy available. Clearer sirtuin signals. sharper audit. Each thing follows from the last. None of it is dramatic. It is bookkeeping, done in the dark, by molecules too small to see and too numerous to count. Mia does not hurry through this part of the floor. She reads slowly, a tagged mitochondrion here, a membrane potential drifting at the edge of the acceptable range there. She notes it. She moves on. She trusts that Alex will collect what she has marked, that Nancy will keep the signals lit, that Ollie is behind her clearing the residue from units already taken offline. They share the work, though not always in the same corridor. It did not make the process elegant. It made it reliable. Nothing is required of you now. Not thinking, not planning, not remembering. All of it can wait until morning. There is something Mia has always found quietly interesting about the way a mitochondrion moves. Not where it travels. Mitochondria do travel, pulled along microscopic tracks inside the cell, sent toward the places that need power most. That part is unremarkable, a kind of cellular logistics. What Mia finds interesting is the shape they hold while they move, and what that shape is trying to say. A mitochondrion is not a fixed object. It is more like a living rope. It extends, it contracts. It fuses with a neighbor, and for a while they become one longer structure, sharing membrane, sharing contents, sharing whatever they have. Then they divide again, pinching off into separate units. The whole family of mitochondria inside a single cell is constantly doing this, merging and splitting, splitting and merging in a slow rhythm that most people never think about. This is called mitochondrial dynamics. And once you understand what it is for, the shape of a mitochondrion stops being a detail and starts being a sentence. Here is what fusion says. When two mitochondria fuse, when they press their outer membranes together and blend into one, they are pooling their resources. A mitochondrion that has taken some damage, one with a small membrane flaw or a few malfunctioning proteins, can dilute that damage by merging with a healthier neighbor. The good enzymes spread through the combined structure. The slightly off-balance chemistry evens out. It is, in its way, a mutual aid arrangement. The struggling unit borrows competence it has temporarily lost. Fusion keeps mitochondria in the game longer. It is the cell's first attempt to rehabilitate before it resorts to recycling. Mia notes this. She does not interrupt it. There is no point flagging a unit that is already being helped. But fusion has a limit. A mitochondrion that is too far gone, one where the membrane potential has drifted too low, one where the damage runs deeper than a passing neighbor can correct. That unit cannot fuse. The very mechanism that would allow it to merge with a healthier partner requires a reasonably intact membrane. A unit below a certain threshold loses that option entirely. And here is the moment that matters. When a mitochondrion cannot fuse, it is forced to divide. It fragments, it breaks away from the network, it becomes isolated, a small separate structure, no longer sharing, no longer borrowing. And that isolation is itself a signal. The cell reads it the way you might read a worker stepping away from the group. Something is wrong. The separation is not random. It is the first step in a deliberate process. Mia knows this. Once a mitochondrion is isolated by fragmentation, the tags Mia depends on begin to accumulate more easily. Pink 1, the protein that builds up on a damaged mitochondrion's outer surface like a slow flag being raised, concentrates there. Parkin, the molecular label that marks the unit for collection, follows. The machinery of mitophagy, the recycling process that takes a worn-out power station offline and breaks it down for parts, is waiting for exactly this shape: small, fragmented, alone, and flagged. Autophagy Alex receives the flagged unit without ceremony. He has prepared for this. His collecting membranes, the flexible structures that will engulf and seal the mitochondrion for processing, form most readily during deep sleep and in the fasting state. Conditions that are, as it happens, both present right now. He does not rush. He simply proceeds. The membrane curves around the fragmented unit, closes, and the recycling begins. The components that come back are not wasted. Fatty acids return to the general fuel pool. Proteins are broken into amino acids that will be used to build the next generation of mitochondrial machinery. Even the iron from certain electron-carrying proteins is recovered. The cell is not sentimental about old equipment, but it is not wasteful either. What comes next from that recovered material is a new unit, smaller at first, running cautiously, its efficiency not yet proven. It will fuse with the existing network when its membrane potential is high enough to qualify. It will share its fresh enzymes. It will pull its weight. Over time, if the conditions hold, it will become one of the reliable ones that Mia passes without stopping. The whole arc, fusion, isolation, fragmentation, flagging, recycling, renewal, is happening across the cell floor right now. Not dramatically, not all at once. The body has no interest in drama at this hour. It has interest in accuracy, in doing the small thing correctly many times over, until the floor is in better shape than it was when the sun went down. Mia walks the floor and reads the shapes. She notes which units are elongated and fused, the ones working well and helping neighbors. She notes the small, fragmented ones sitting alone with their flags up. She does not need to do much. The system already knows what it is doing. Her job is attention. To confirm that the signals mean what they are supposed to mean, that the right units are being taken offline and not the wrong ones. This is what quality control looks like when it is working, not intervention, not repair done in a hurry, just steady, methodical reading of what the cell is already saying. It did not make the process glamorous, it made it honest. Your hands are open and resting. Your feet are warm. The whole body is settling, one small piece at a time. So the worn one is gone, wrapped, broken down, returned to parts. And a natural question rises in the quiet. Where does the next one come from? The answer is one of the more satisfying things the cell does. It builds fresh mitochondria, largely from what the old ones left behind. The amino acids, the membrane fats, the mineral cofactors, all of it recovered, sorted, and handed back to the production line. Nothing is wasted here. Mia has seen this cycle run so many times that the elegance of it has settled into something like background music. She notices it the way you notice a well-run kitchen, quietly, with approval. The process of making new mitochondria has a name: biogenesis, meaning simply the making of new living machinery. The cell does not manufacture them from scratch, the way a factory stamps out parts. It grows them. It divides existing mitochondria, extending what is already there. A healthy mitochondrion that has kept its membrane potential, passed its fusion tests, and shown no accumulation of pink one. That one earns the right to divide. It pinches inward along the middle and separates into two. Both carry forward a working copy of the inner architecture. Both carry forward a working copy of the mitochondrial genome, the small separate loop of genetic instructions that mitochondria carry on their own, independent of the cell's nucleus. That last part is worth a slow breath. Mitochondria have their own DNA, not much, just enough to code for a handful of the proteins that run the inner membrane machinery. The rest of the proteins needed are encoded in the cell's main nucleus and imported later. But that small separate loop of instructions is a remnant of a very old relationship. Somewhere far back in the history of life, a mitochondrion was a free-living bacterium. It moved inside another cell, and neither of them ever left. The relationship deepened over so much time that the two became inseparable. The mitochondrion kept its own genome as a kind of quiet signature, and the cell kept it warm. Mia knows this, in the way that knowing something changes how you carry it. Every mitochondrion she audits is ancient in that sense. Every worn one she flags for recycling is the latest chapter in a story that began before anything had a spine. None of that sentiment changes the audit. The flagging still happens. The recycling still runs, but it gives the work a different weight. Now, the making of new mitochondria does not run on goodwill alone. It needs a signal. It needs something to tell the cell that new production is authorized, that the conditions are right, that energy demand and fuel supply are balanced enough to support the investment. That signal runs through a molecule called PGC1 alpha, a name worth keeping only long enough to understand what it does. Think of it as a master switch for mitochondrial production. When PGC1 alpha is active, the genes responsible for building mitochondrial parts get turned on. The cell begins assembling the proteins for new inner membranes, new electron-carrying complexes, new matrix enzymes. What turns PGC1 alpha on? Exercise is one thing, but that is the day's business. Here, in the sleeping body, two other signals matter. When fuel intake has paused, a sensor molecule in the cell called AMPK, a kind of low fuel warning system, becomes active, and AMPK can switch PGC1 alpha on. The overnight fast that begins when eating ends is exactly the kind of sustained, gentle fuel pause that nudges this pathway, not a dramatic shortage. Just the ordinary quiet of a body that has stopped eating and begun drawing on its stores. The other signal is NAD+, Nancy, working again. The sirtuin enzymes she fuels can activate PGC1 alpha directly. When Nancy's supply is adequate and sirtuins are running at full sensitivity, the instruction to build new mitochondria moves cleanly through the system. When her levels drift low, as they tend to do across a lifetime, the signal softens. The instruction still gets through, but more slowly, less sharply. It is more like a voice that has grown a little quieter and needs the room to be a little stiller to be heard. Sleep provides that stillness. Autophagy Alex, running his recycling operations in the deep sleep window, passes recovered components toward the biogenesis line with the unhurried efficiency of someone who has prepared the workspace in advance. He does not rush. He has no interest in rushing. He runs best in exactly these conditions. Fuel low, demand quiet, the cell finally free to attend to its own interior. Mia moves through this part of the floor with a different pace. The audit is still running, still flagging, still marking the worn units for collection. But alongside it, just a few steps away, the new ones are growing. It is the same floor, the same hour. Two directions of the same process. The old leaving, the new arriving, happening not in sequence, but in parallel. The cell does not wait for the audit to finish before it starts building. It builds while it clears. It renews while it recycles. That is not inefficiency. That is the only way a system this busy can stay ahead. It did not make the floor feel hopeful. It made it feel continuous. The mind is allowed to wander off mid-sentence. Let it. There is nothing here you have to keep hold of. There is a molecule in the cell that does not build anything. It does not carry oxygen. It does not wrap failing mitochondria in membrane or ferry electrons down a relay chain. What it does is simpler, and in some ways more important than any of those things. It listens. The molecule is called AMPK, adenosine monophosphate activated protein kinase, if you want the full name, though the full name is not the point. Specifically, it reads the energy level of the cell. When ATP, the small energy-carrying molecule, the mitochondria spend their working lives producing. When ATP runs low in its spent form, AMP begins to accumulate. AMPK stirs, it registers the imbalance. And then it tells the rest of the cell what it found. Think of it as a gauge on the wall of the engine room. Not the engine itself, not the fuel, just the gauge. Quiet and accurate and always watching. Mia knows this. She has seen AMPK trigger things that look, from the outside, like decisions. When energy runs low, AMPK does not raise an alarm. It simply adjusts. It turns off processes that spend energy and turns on processes that make it. It signals PGC1 alpha, the master switch for building new mitochondria, to start work. It sharpens the recycling signals that tell autophagy Alex which units are ready for collection. It even nudges NAD plus Nancy into pathways that amplify sirtuin activity, the enzymes that help Mia flag the most worn power stations with greater precision. All of this happens quietly. No announcement. The system responds. And here's the thing about sleep and fasting that most people do not think about in this way. When you have been asleep for a few hours and have not eaten since the evening, the body is running on its reserves. The steady supply of glucose from the last meal has slowed. Insulin, the hormone that carries sugar into cells, has quieted. The cell is drawing on stored fuel, fat broken down into fatty acids, glycogen converted back to glucose, ketones rising slowly in the blood. It is not a shortage. It is a shift. And that shift is exactly the condition AMPK was built to read. In that shift, the energy gauge dips just enough, not dangerously. And AMPK reads it, and the recycling and renewal systems come to full attention. This is why the night matters for this particular kind of work. Not because the body is doing nothing. Because the demand has dropped and the gauge has moved, and that movement is the permission slip. Mitophagy does not run well in a cell that is busy meeting every immediate request. It runs well in a cell that has a little slack, a little space between what is being asked of it and what it has available. Mia walked past a cluster of recently formed mitochondria near the inner membrane of a muscle cell. They were small and dense, as new ones tend to be. Their membranes were tight. Their proton gradients, the electrical charge across the membrane wall that drives ATP production, were steep and clean. They had come from last week's recycling, in a sense. Raw material recovered from worn units, fed back into the pool, assembled into something new. She did not linger on them. She noted them the way an auditor notes a clean ledger, with brief professional satisfaction. Further along the floor, AMPK's signal was still moving through the cell like a slow current. It had already reached the enzymes responsible for fatty acid oxidation, breaking down fats for fuel, and turned them up. It had flagged a handful of protein-building operations that could wait until morning and asked them to pause, not permanently, just until the energy picture improved. The cell was not reducing itself, it was reprioritizing. Maintenance over production, renewal over output, the quiet work over the busy work. Ollie, the night janitor, was working 3 organelles over. He had found the remnants of a reactive oxygen species, a free radical, one of the small unstable molecules that leak from worn mitochondria and cause molecular damage if left unchecked, and was already neutralizing it. His antioxidant enzymes moved over the damage with the unhurried efficiency of someone who has done this every night for years. The damage was minor. The leaky unit that had produced it was already flagged, already wrapped, already in Alex's queue. That is how the loop closes. Mia flags, Alex collects, Ollie cleans. AMPK watches the gauge and keeps the permission slip valid through the night. No single one of them could manage alone. The gauge means nothing without the recycler. The recycler is blind without the flags. The flags are blurry without Nancy carrying enough electrons to keep the sirtuin enzymes sharp. And all of it, the whole quiet system, idles during the busy hours of the day and comes to life in the silence. Mia knows this hour. The cell floor was neither loud nor still. It was the particular kind of occupied that good systems fall into when conditions are right. Purposeful, low, continuous. The gauge on the wall read slightly below its midpoint. AMPK's signal moved through the cytoplasm like a tide that does not rush. It did not make the work feel urgent. It made it feel earned. Deeper now. Softer now. The breath keeps its own slow time, in and out, without any help from you. There is a moment in any long shift when the work stops being about what you are doing and starts being about what you can see. Mia had reached that moment. The audit was running smoothly. The flags were placed. The wrappers were closing. Alex was moving at his quiet pace through the recycling lanes. But now she paused at a corner of the cell floor that looked different from the rest. Not broken exactly, not flagged, just older looking, with a quality that was harder to name, a kind of molecular tiredness that showed up not in any one place, but in the cumulative record of everything that had happened here. This is where Ollie came in. Oxidative Ollie, to give him his full name, is the cell's night janitor, and his specific assignment is something the daytime crew never quite handles. During the hours when mitochondria are running hard and producing energy, they release a byproduct. Not waste exactly, more like sparks. Tiny, highly reactive molecules that fly off the machinery during the process of making ATP. Chemists call them reactive oxygen species. Ollie calls them tiny arsonists. They are not malicious. They were never meant to cause harm. They are simply a side effect of running an electron relay at speed. The same way a wood fire produces heat and also embers that drift. On a good night, Ollie is well ahead of them. He carries the tools, enzymes with names like superoxide dismutase and catalase, that intercept the reactive molecules and neutralize them before they can wander into the wrong places and scorch something important. A strand of DNA, a protein that folds just so, the outer membrane of a mitochondrion that is otherwise still doing fine. On a night like this, with the body well rested and the fasting state deepening, Ollie had good odds. The worn units had already been flagged and were being processed. The healthy ones were sealed up tight, running clean. The sparks were few. But here, at this corner of the cell, the record told a slightly older story. A mitochondrion that runs leaky does not just produce less ATP, it also produces more sparks. The electron relay inside it has gaps, places where electrons slip sideways instead of moving cleanly along the chain, and every sideways slit becomes a reactive molecule looking for somewhere to land. So a worn unit is doubly costly. It gives less while it takes more, and while it takes, it scatters sparks across everything nearby. The damage left behind by a leaky unit is part of what she reads when she is deciding how long a neighboring unit has been running in poor conditions. Ollie's work leaves a kind of record too. The places where he has been scrubbing longest are the places where the sparks were most frequent. And the places where sparks were most frequent are almost always the places where a worn mitochondrion was running unchecked for too long. It is not a conversation they have. It is more like reading the same book from different chapters. Ollie sees the sparks. Mia sees the source. Between the two of them, the full picture assembles itself quietly. There is a word for what Ollie is defending against on the larger scale. Oxidative stress, meaning the state when reactive molecules are being produced faster than they can be neutralized, leaving a cumulative record of small damage across proteins and membranes and genetic material. It does not arrive like a sudden event. It accumulates slowly, the way a room gets dusty, not dramatically, not all at once, just a steady drift that takes time to notice and more time to clear. Sleep is part of how the clearing happens. The daytime workload generates the sparks as a natural byproduct of energy production, and the body handles most of them well, but the handling is not perfect. Some damage always gets ahead of the cleanup. And so the hours of rest, when energy demand drops, when the sparks are fewer, when Ollie has room to work without being immediately outpaced, are the hours when the balance tips back toward clean. What Mia was reading at this corner of the cell floor was the near end of a recovery. The worn unit had been flagged and collected hours ago. The components were already moving back into circulation, and Ollie had been working through the aftermath, the molecular residue of all those extra sparks, in the steady, methodical way he always worked. Not fast, not dramatic, just relentlessly thorough. The corner looked tired because it was finishing its recovery. By morning, it would look like the rest of the floor. Mia stood there for a moment longer than she needed to. This was the part of the audit that no single process could account for. Not the flagging, not the wrapping, not the biogenesis, not the antioxidant work. The cell did not recover in a straight line from one worn unit to a fresh one. It recovered in layers, old damage cleared while new parts assembled, reactive sparks neutralized while membranes resealed. The inventory of what was broken slowly shrinking, while the inventory of what was ready slowly grew. The body did not wait for everything to be finished before moving on. It ran all of it at once, each process reading the outputs of the others, adjusting, compensating, moving toward a state that was not perfect, but was continuously improving. Mia knows this hour. The cell floor at Deep Sleep was not a repair shop with a single workbench. It was more like a quiet city in the early morning. Dozens of crews working their separate lanes, each one contributing to something none of them could complete alone. It did not make the work feel simple. It made it feel whole. Your arms are heavy. Your legs are heavy. That heaviness is the good kind, the kind that means the day is finally over. There is a moment in any repair operation when the work shifts. The finding is done, the flagging is done, the old parts are on their way out. And what remains is the question of what comes next. Not philosophically, practically. Where does a new mitochondrion actually come from? She has stood at this threshold more times than the cell could count. The answer is not a warehouse. There is no stockroom somewhere in the cell, neatly shelved with fresh mitochondria still in their packaging. The cell does not work that way. What it has instead is something more patient and more elegant. It builds from what it recovers, and it copies what is still good. Here is the thing about mitochondria that most people never hear. They have their own DNA, a small loop of genetic instructions, separate from the master blueprint stored in the cell's nucleus. That is unusual. Almost every other structure in the cell relies entirely on the nucleus to tell it what to be. Mitochondria carry a piece of their own code. It is a remnant, biologists believe, of a very old arrangement, a time unimaginably distant, when the ancestors of mitochondria lived as separate organisms before being folded into a larger cell. And so the loop of instructions remained. What this means for Mia's work is specific and practical. When a healthy mitochondrion divides, when it splits itself into two, both capable and both carrying that small loop of code, it is not waiting for directions from above. It is running its own quiet duplication. The cell signals the need. The healthy mitochondria respond by dividing. And the division produces units that are, from their first moment, ready to join the floor. NAD+. Nancy makes this possible in ways she rarely slows down to describe. The energy that drives the replication of that mitochondrial code, the assembly of new membranes, the construction of the protein complexes that will run the electron relay, all of it costs something, and much of that cost moves through Nancy's electron-carrying capacity. She is, as she would say if she were the kind of molecule to say things, present at every stage. She finds this neither remarkable nor burdensome. It is simply the nature of the work. Growth hormone Greg, working one floor up, also plays a part here, quieter than his main work of rebuilding muscle and managing fuel. The hormonal signals that Greg's release into deep sleep sends through the body include ones that nudge PGC1 alpha, the master switch for new mitochondria, a little further open. Greg does not build mitochondria directly, but the conditions he helps create during deep sleep are the same conditions in which mitochondrial renewal runs most freely. They share the work, though not always in the same room. And then there is the question of the recovered material. When autophagy Alex processes a mitochondrion that Mia has flagged, wrapping it carefully in that double membrane, breaking it down by degrees, what emerges from that process is not waste. The proteins are disassembled into their amino acid components. The lipids are recovered. The minerals and the molecular building blocks that the membrane complexes were made of go back into the cell's common pool. Raw material, usable again. This is the recycling that Alex does best. He has a phrase for it, quiet and without drama. The old unit funds the new one. He finds the efficiency satisfying in a way he does not need to explain. Nothing is discarded that can be recovered. Nothing is lost that was still useful at the molecular level. The worn engine is gone, but its parts are not. Mia walks this stretch of the floor slowly. There is something worth noticing here. Something that does not always get its due. The cell is not simply removing the old and replacing it. It is running both processes at once, linked at the material level. The same fasting state that deepens Mia's mitophagy signals also amplifies PGC1 alpha, the signal that starts new mitochondria forming. The same sleep that gives Alex the quiet he needs to run his operation is the sleep in which the healthy mitochondria are most likely to divide and duplicate, cleaning and building, recycling and renewing, not in sequence, in parallel, on the same floor, in the same window of rest. Ollie passes Mia on his round, trailing the faint chemical signature of the antioxidant enzymes he has been deploying near the recently cleared units. He does not say anything. He rarely does at this hour. But the absence of new reactive oxygen species near the freshly cleared zones is its own kind of report. The leaky sources are gone. The damage trail is shorter. The new units coming on will run clean, at least for a while. Mia marks the section in her ledger, not with any ceremony. A notation, a boundary line between what was reviewed and what comes next. She has done this work long enough to know that the two halves of renewal, clearing the old, building the new, are not really separate. They are the same process, viewed from different angles. One ends where the other begins, and the material flows between them without interruption. It is the hour when the cell is most purely itself, not producing, not defending, not responding to demand from outside, just quietly doing the thing it was always designed to do. It did not make the work feel lighter. It made it feel like enough. Let the jaw unclench. Let the space between the eyebrows go smooth. Small places hold the day longest. There is a place in the body where the demand never stops. The heart does not rest the way a muscle rests. It cannot. It squeezes and releases somewhere around 100,000 times a day, every day, without negotiation. The cells that make that possible, the cardiomyocytes, meaning simply the heart's own muscle cells, carry more mitochondria per cell than almost anywhere else in the body. Not because the body is being generous, because the work requires it. A single heart muscle cell can hold mitochondria packed so densely they account for roughly a third of its entire volume. The space is not wasted on storage or scaffolding. It is engine room floor to ceiling. Mia knows this. She has walked this particular corridor many times. And what strikes her every time is not the density of the machinery. It is the precision of the arrangement. In most cells, mitochondria drift and rearrange as needed, fusing, dividing, repositioning themselves closer to wherever the demand is highest. Heart muscle cells do not have that luxury. The mitochondria here are fixed in place, locked into tight rows alongside the contractile fibers they power, like generators bolted directly to the machines they run. They cannot wander, they cannot reposition. When one of them begins to fail, it cannot even drift away from its neighbors for a quiet exit. It fails in place. This is why the quality control work in a heart cell is so particular. In most tissues, a worn mitochondrion loses the ability to fuse with its neighbors, fragments into isolation, and floats toward autophagy Alex's collection point through the general motion of the cell's interior. In a heart cell, that path is compressed. The space between mitochondria is measured in fractions of a micrometer, a unit so small that placing 5,000 of them end to end would barely span the width of a human hair. There is almost no room to maneuver. The flagging still happens. The pink 1 and Parkin signals still accumulate on the outer surface of a worn unit. But the handoff to Alex requires a kind of careful threading that is not necessary in less crowded tissue. What the heart relies on instead is extraordinary selectivity. The mitophagy signals here must be sharp, not approximate. A worn mitochondrion in a heart cell sits so close to a healthy one that the machinery clearing it has to be precise enough to take the failing unit without disturbing the one beside it. This is the difference between removing a single loose brick and pulling one from the middle of a load-bearing wall. The structure depends on every neighboring unit remaining in place, while the compromised one is extracted and handed over. NAD plus Nancy understands the weight of this. The sirtuin enzymes she powers, the ones that read the cell's metabolic state and sharpen the mitophagy signals, are in heart muscle doing work that has almost no margin for error. Nancy does not describe it that way. She is too busy carrying electrons to editorialize. But the precision of the signals she enables in this tissue is measurably different from what she supports elsewhere. The selectivity is finer. The threshold is more exact. Ali, meanwhile, runs his tightest circuits here. A leaky mitochondrion anywhere in the body is his problem. A leaky mitochondrion in a heart cell, packed against its neighbors with no room between them, produces reactive molecules that arrive at the adjacent membrane almost before Ali can intercept them. He has learned to run ahead of the accumulation in this tissue rather than behind it. Not because he anticipates it, he simply knows the geography, and he positions his antioxidant resources accordingly. And this is where something remarkable comes into focus. The body made a structural choice when it built the heart. It packed those cells so tightly with mitochondria that efficiency became the room's only decoration. But that same density meant the maintenance systems had to become correspondingly exact. Mitophagy here is not a loose sweep of the floor at the end of the day. It is a precise extraction, unit by unit, conducted in almost no working space, during the narrow window that sleep and the fasting state open. Greg, working his own repair cycles in the tissue surrounding the heart, keeps the larger structure intact. Mia works the interior of each cell. The scales are different. The patience required is about the same. What sleep gives the heart cells is time with reduced demand. The heart still beats during sleep, slower, steadier, the rate dropping into a gentler rhythm. The mitochondria are still running. But the ATP demand is lower, and that lower demand means the maintenance signals, AMPK reading the relative quiet, PGC1 alpha responding, sirtuin enzymes sharpening their read, have more room to operate without competing with the full force of the heart's waking workload. Mia marks 2 units in this row. She works slowly, deliberately, the way the tissue requires. She does not hurry the handoff to Alex. She waits until the signal is clean and the path is clear. The cardiomyocyte around her does not register the procedure. It goes on beating its slow, sleeping rhythm. 70, 65, 60 beats per minute. The sound of a body genuinely at rest. Mia knows this hour. The heart asks the most of its engines. It asks the most of the systems that keep those engines honest, too. It was not a complaint. It was just the geometry of the work. This is the easiest part of the whole day. Nothing to carry, nothing to finish, only rest and the quiet dark. The heart is not the only demanding neighborhood on Mia's route. She moves on, and the next address on her audit is, in its own way, even more remarkable. Neurons, the long branching cells that carry thought and sensation, and the signals that keep everything else coordinated, are among the most energy-hungry cells in the body. They do not rest between tasks the way a muscle fiber does. They fire constantly, adjusting, receiving, sending. And a firing neuron is a cell that never stops spending ATP. So neurons carry mitochondria the way a traveler carries extra batteries. Not just at the center of the cell where the nucleus sits, but out along the branches, the long thread-like arms called axons and dendrites that extend outward to touch neighboring cells. Some of those branches stretch an extraordinary distance by cellular standards. A single neuron running from the base of your spine down toward your foot can be more than a meter long. That is a very long way to send a power station. And that distance is where Mia's work becomes, in her own quiet estimation, genuinely interesting. Here is the thing. A mitochondrion sitting at the far end of a long axon is a long way from the recycling machinery. Autophagy Alex works well, but he is not everywhere at once. When a mitochondrion at the tip of a distant branch wears down and loses its membrane potential, when pink 1 begins to accumulate and Parkin tags the outer surface, the signal still needs to travel. The worn unit needs to make its way back toward the cell body where the full recycling apparatus is concentrated. The cell has a transport system for exactly this. Small molecular motors, tiny protein machines that walk along internal tracks called microtubules, carry mitochondria in both directions. Healthy units travel outward toward the active tips where ATP demand is highest. Worn ones travel back toward the center where Alex can process them. Turns out that the direction a mitochondrion travels is not random. It is decided by its condition. A healthy mitochondrion with strong membrane potential tends to move outward or stay put, anchored where it is needed. A worn one, with its potential flagged low, tends to detach and move inward. The molecular motors read the signal, and they route accordingly. Mia knows this. It is a quieter version of the same logic that governs everything else on the floor. Condition determines destination. The cell does not move parts randomly. It routes them. Now add one more layer. Neurons are unusual in another way. They are, for the most part, cells the body does not replace. Most tissues turn over. Old cells retire, new ones grow in. Neurons in the adult brain are largely the same cells that have been there since early life. They do not divide and refresh the way liver cells or skin cells do. So when a neuron sustains damage, it cannot simply be replaced from a fresh supply. This makes the mitochondrial audit inside a neuron more consequential than almost anywhere else in the body. A worn mitochondrion that leaks reactive oxygen species in a liver cell does damage. Ollie cleans it up, Mia flags the unit, Alex recycles it, and in time, a fresh cell may replace the old one anyway. In a neuron, the cell itself stays. Only the mitochondria inside it can be refreshed. Mitophagy, in the brain, is one of the few renewal mechanisms the neuron actually has. NAD+. Nancy's role here is worth sitting with for a moment. The sirtuin enzymes she powers do not just sharpen mitophagy signals. In neurons specifically, they support the molecular machinery that maintains the health of axons, the long arms where mitochondria must travel farthest. When Nancy's carrying capacity is high, the entire transport and recycling system runs with more precision. When it drifts lower, as it tends to do across a long day of firing and spending, the sensitivity of those quality control signals softens. Sleep, and the fasting state that tends to accompany it, allows Nancy's levels to recover. AMPK reads the lower ATP and nudges the cell toward maintenance. PGC1-alpha begins to signal new mitochondrial growth, and the molecular motors on the microtubule tracks carry their passengers in both directions, fresh units outward to waiting dendrites, worn ones inward toward Alex's careful hands. Ollie works the edges of this neighborhood too. The farther a mitochondrion sits from the cell body, the farther its reactive byproducts are from the cell's main antioxidant reserves. A leaky unit at the tip of a long axon is a small fire, a long way from the nearest bucket. So Ollie keeps mobile reserves distributed along the length of the neuron, antioxidant enzymes stationed like outposts rather than concentrated at headquarters. He is practical about it. You work with the geography you have. Mia finishes her read of the outer branches and notes the units that have been correctly routed inward. A few are already in transit. The molecular motors have done their part. By the time Alex processes them, their components will be ready to join the common pool: amino acids, lipid fragments, the raw material from which new membranes will be built. The long axon is not a problem the cell solves once and forgets. It is a standing logistical challenge met quietly every single night while the neuron sires its last slow signals and the brain settles into the deeper layers of sleep. It did not make the work easier. It made it worth doing. You are further from waking now than you were a few minutes ago. That is the whole direction of travel. Just down and quieter. There is a structure inside every cell that most people never hear about. Not the nucleus, not the mitochondria. Something more like a skeleton, a fine branching lattice of protein filaments that fills the interior and holds everything roughly where it belongs. The cell has its own scaffold. And Mia, walking the floor as she does each night, walks it. This inner framework goes by a name that sounds technical, but really just means what it does. The cytoskeleton, meaning the skeleton of the cell. It is not rigid the way bone is rigid. It shifts. It remodels. It extends a filament here, pulls one back there, and in doing so it moves things. Organelles, vesicles, the molecular motors that carry cargo from one address to another. Everything inside a cell that needs to be somewhere is, more or less, because the cytoskeleton brought it there. Mitochondria are no exception. They are not floating freely, drifting wherever the fluid of the cell takes them. They are anchored, tethered, in some cells, like equipment bolted to a factory floor. In others, they travel, carried along cytoskeletal filaments by small motor proteins the way packages move along a conveyor belt. The filaments are the belt, the motors are the carriers. The mitochondria are the packages, and here is where the night matters in a way that is easy to miss. During the day, when a cell is active and its energy demand is high, the cytoskeleton is biased toward keeping mitochondria near the places that need ATP most. In a muscle cell, near the contractile fibers. In a neuron, out along the axon at the synapses, where the signaling happens. The framework is organized around output, around meeting demand as fast as it arrives. When demand drops, when the body settles into sleep and the fasting state begins to deepen, the cytoskeletal bias shifts. It is subtle, but it is real. The scaffolding that held mitochondria tightly in their working positions relaxes its grip, just enough. And that small change in tension is what allows something important. The worn units can be moved. Mia knows this. A mitochondrion that has already been flagged, its outer surface tagged by Parkin, its pink 1 signal still active, needs to reach a place where autophagy Alex can collect it. Alex does not come to it. The autophagosome, the membrane envelope Alex uses to wrap and transport worn organelles, forms around the flagged unit. But the flagged unit still has to be accessible. It has to be in a position where the wrapping machinery can reach it. And in a dense cell, a heart muscle cell packed with contractile fibers, a neuron with mitochondria stationed far from the cell body, that accessibility is not guaranteed by default. The cytoskeleton is what makes it possible. In the reduced demand state of sleep, motor proteins on the filaments begin routing flagged mitochondria toward the cell's interior, toward the regions where autophagy machinery tends to concentrate. It is not a dramatic migration. It is a slow reorientation. But it is enough. The warn unit arrives at the right address, and Alex is already there, ready. There is something quietly elegant about this. The same scaffold that positioned mitochondria for maximum output during the day repositions the worn ones for recycling during the night. It is the same structure, serving two opposite purposes at two opposite times without contradiction. NAD plus Nancy keeps this process honest. The motor proteins that move cargo along cytoskeletal filaments need energy to run. Not much. They are efficient machines, but they need some, and the currency they spend is ATP, generated by the healthier mitochondria, still running their steady maintenance current. Nancy's electron carrying capacity sustains that current. Without it, the motors slow. The worn units stall in place. The recycling queue backs up. Ollie, meanwhile, has his own relationship with the cytoskeleton. Some of the antioxidant enzymes he depends on, the ones that neutralize reactive oxygen species close to where they form, are anchored to cytoskeletal filaments, positioned near mitochondria on purpose. They are not floating, waiting to be needed. They are already there, already at the crime scene, as Ollie would put it, before the sparks arrive. When a mitochondrion begins to fail and its reactive molecule output climbs, the antioxidant coverage nearby catches the first wave. Ollie's enzymes absorb the excess, but the flagging by Pink 1 and Parkin is also climbing. The cytoskeleton begins routing the unit inward. Alex's machinery is assembling nearby. All of it. The damage control, the flagging, the transport, the collection, is happening in the same local neighborhood of the cell, coordinated not by any central command, but by shared chemistry and shared proximity. The cell does not have a manager. It has conditions. And the conditions of sleep, low demand, sustained NAD plus availability, AMPK's maintenance signal running, the fasting state holding, set every part of this system to the same quiet frequency at once. Greg is working somewhere above, rebuilding tissue at the scale of fibers and membranes. Mia is here, one level down, ensuring the engines inside those fibers are worth keeping. They do not need to coordinate. The night coordinates them. It did not make the scaffold simpler. It made it purposeful. Notice the weight of your head on the pillow. Heavier than you thought. Let it be that heavy. And so the work continues. Not loudly, not urgently, just steadily, the way water moves in a deep, slow river, always moving, never rushing. Mia is still walking the floor. She has been here for hours now, reading the signals, checking the flags, passing the worn ones along to Alex, who wraps them quietly and begins the long, patient work of taking them apart for parts. It is good work, unglamorous work, the kind that never gets announced. But the cell knows. The cell feels the difference between a floor full of tired, leaking engines and one where the worn ones have been taken offline, where the fresh ones are running clean. Mia knows this. Nancy is still moving through the cell, carrying her electrons from one reaction to the next. She does not slow down. She does not need to be told. The fasting state, the deep quiet, the long hours without food or noise or demand, these are her best conditions, and she uses them. The sirtuins she powers are still tuning the signals, still sharpening the flags, still making sure that what gets marked for recycling is truly ready to go, and what gets spared is truly worth keeping. This is the part of the night that most people never think about. Not the falling asleep, not the dreaming, but this, the quiet hours after, when the cell is finally free of the day's demands and the real work of renewal gets its turn. Ali is moving through the corridors. He is still mopping up behind the worn units, still neutralizing the small sparks they left behind before Mia flagged them. He does not rush either. The night is long enough. The antioxidant reserves are holding. He moves with the easy confidence of someone who has done this shift many times before. And somewhere above, Greg is still working. Rebuilding the larger structures, the beams and walls of the body, as he would say. He and Mia work at different scales, but they share the same conditions, the same quiet, the same window that only opens when the body is truly at rest. They share the work, silently, professionally. The heart cells are quieter now, not stopped, never stopped, but running at their lowest possible demand. Each beat a little slower than the last few hours of waking. The mitochondria packed in those tight, ordered rows have a little more room, a little more time. Mia's sharpest signals have done their work there. The worn ones are already gone, already in Alex's careful hands. Out along the long branching arms of the neurons, the transport motors are still moving, still carrying the last of the flagged units back toward home. It is a long journey, but the scaffold is in place. The tracks are clear. The motors have what they need. Nancy sees to that. And in the recycling stations that Alex has been running all through these deep hours, the raw material from the worn mitochondria is already being sorted, membrane fragments set aside, proteins disassembled gently into their components, the building blocks returning to the common pool, ready to be shaped into something new. This is the part that stays worth thinking about, even half asleep. Nothing is wasted. Not the worn membrane, not the tired protein, not the electron carrier that can no longer carry as cleanly as it once did. All of it becomes material. All of it goes back into the floor, and what comes out of the floor in time will be fresh and efficient and ready. The cell is already building new mitochondria from what it has recovered. Quietly, under the instruction of PGC1 alpha, which is still receiving its steady signal from AMPK, which is still reading the fasting state, which persists for as long as the body rests. One process feeding the next, one signal enabling the one beside it. Not a chain exactly, more like a conversation. A long, slow, thoughtful conversation that the cell has been having with itself all through these hours. Mia knows this dark. She has always known this part of the night. The part where the audit is nearly done, where the floor has been walked and most of the flags are placed, and most of the worn ones are already on their way. There is a particular kind of quiet that settles over a cell in this hour. Not emptiness, not stillness exactly. Just readiness. The readiness of a floor that has been tended, of machinery that has been reviewed, of a body that has been given the hours it needed to do the work that the day never allows. The night is still here. And so is Mia. Let the back settle into the mattress. Let it take your weight completely. It has been waiting all day to do that. The night is still here, and so is Mia. She moves the way she always moves in this hour, quietly, without hurry, one station at a time. The cell floor is dim now. The day's demands have been quiet for a long while. The traffic that made everything rush and surge and spend has settled into something much more gentle. And into that gentleness, the work continues. Mia checks a membrane, reads its quiet signal, moves on. She has done this 1,000 times on 1,000 nights, in 1,000 cells across the body. She will do it again. That is the whole of the job, and somehow it never becomes ordinary. Not far from where she walks, Mitophagy Alex is still at it. No announcement, no fanfare, just the steady, patient wrapping of what needs to go. A worn unit gets enclosed, the membrane seals. The process continues. Alex finds the rhythm of late night deeply agreeable. Conditions are right. He sees no reason to rush. Somewhere along the cell's inner scaffolding, NAD plus Nancy is still carrying her electrons, still passing them forward, still fueling the quiet enzymes that keep the signals clean and the audit sensitive. She has been at this since the day began, and she will keep at it until the light comes back. That is simply what she does. And Ollie is out there on the cell floor working in the dark the way he always works, clearing the last small sparks, moving along the filaments where his tools are stored. He does not need to see the big picture. He only needs to find the next reactive molecule and take it somewhere it cannot cause harm. One more, and one more after that. Up! At the structural level, Greg is still building, quietly laying down what the day tore through. He works up a scale of beams and fibers and walls. Mia works at the scale of engines. Different floors, same building, same quiet dedication to a body that is finally fully resting. Mia knows this hour. She knows how the cell feels when the work is going well. The membrane potentials holding steady on the healthy units. The worn ones already handed off to Alex, already becoming raw material again. The new units, still small and fresh, beginning to find their place along the cytoskeleton. This is the floor at its best. Not finished, not perfect, just honest and working. In the heart muscle, the densely packed rows of power stations sit in their careful arrangement. Mia has already been here. She walked this part of the floor earlier in the shift, checking the tight geometry, reading the fine signals, noting which units needed to go. The ones she flagged have been collected. The ones she passed are still running, steady and clean. In the long, quiet corridors of the neurons, the molecular motors have carried their worn cargo slowly back toward the recycling centers. That journey takes time, but the night is long. There is time. The body has always known this. That is why it made the night long enough. Everywhere the same chemistry is running. AMPK reading the low fuel. PGC1 alpha keeping the renewal program open. The sirtuins, fueled by Nancy, sharpening every signal that needs sharpening. And Mia, still walking, still reading, still passing judgment on one small engine at a time. Not one of these processes is loud. Not one of them announces itself. They are the definition of unglamorous work, the kind that only matters because it never stops. The breath in the room is slow now, even and easy. The weight of the body against the mattress has settled into something completely still. And inside that stillness, the cell floor hums, not loudly, barely at all, just enough to signal that the machinery is doing what it was always meant to do when the day finally steps aside. Clearing, renewing, getting ready. Mia takes one more step, reads one more signal. The floor is quieter than it was an hour ago, cleaner, a little more honest. She is not finished, but the night is doing what it does best. Mia knows this. Feel how still the room has become. Warm and quiet and safe. Nothing here needs your attention. Nothing here is asking anything of you at all. The audit is nearly done. Mia has walked every corner of the floor. She has read the faint signals of worn membranes and steady ones. She has left the healthy units running. She has flagged the ones that needed flagging. Alex has wrapped and collected. Nancy has kept the current moving. Ollie has cleared the last faint sparks from the surfaces they left behind. And Greg, one level above, has been doing what he always does, rebuilding the beams and walls while the engine room works quietly beneath him. Not a mission accomplished, not a race won, just a night's work, finished the way good work always finishes, gradually, without announcement. The cell floor is a little cleaner than it was at dusk. The worn units are gone. The new ones, grown from recycled parts and from the quiet division of healthy ones, are still small, still finding their place in the arrangement. They do not yet carry the full load. They do not have to. Morning is a few hours away, and the floor has time. Mia moves through this last stretch without urgency. The fasting chemistry is still holding. AMPK is still keeping the cell in its maintenance posture. The sirtuins, fed by Nancy's steady electron carrying, are still reading the quality signals with their full precision. All these antioxidant enzymes are anchored along the cytoskeleton, waiting for any stray reactive molecule that wanders past. The conditions that made all of this possible are still here, and they will stay until the morning light begins to shift the chemistry back toward action. There is something almost patient about it. The cell does not hurry toward morning. It simply continues, clearing, renewing, holding the quiet, because this is the only window in which that work runs cleanly. And the cell has learned, across a very long history, not to waste it. Mia knows this dark. She has known it in heart cells packed tight with mitochondria, and in neurons reaching their long arms toward distant places, and in every ordinary cell that simply needed its engine room to run a little more honestly by morning. The work is the same everywhere. Remove what is worn. Return the parts. Let the new ones begin. Hold the conditions long enough for all of it to matter. The floor settles. The signals quiet. The body rests. While you sleep, Mitochondria Mia is already at work. She is moving through the cell floor right now, reading the faint chemical signatures of each small power station, the ones still running cleanly, the ones ready to be retired, the ones just beginning to take their place. She is marking the worn units so Autophagy Alex can collect them. She is signaling the healthy ones to divide. She is letting NAD plus Nancy keep the sirtuin enzymes sharp and the motor proteins moving. She is letting Ollie clear the last faint traces of oxidative sparks from the surfaces left behind. All of it is happening without a single instruction from you, in the deep and ordinary dark. You don't have to do anything. Your body knows exactly what to do. It's been doing this work for your entire life, every single night. So let it. Trust it. And as you drift deeper now, Mitochondria Mia will be here when you wake up. Quieter, calmer, better.